Welcome to Lecture 19, Evolution of Low Mass Stars, Part 3. So this is the third and final lecture on the subject of the evolution of low mass stars. In the last lecture, we actually did wrap up our discussion of the evolution of isolated low mass stars. But as I mentioned, it turns out that there are some wrinkles in that evolution that can be introduced by virtue of a star having a binary or even a tertiary partner. And as I've mentioned before in the class, it turns out that a majority of stars in the universe actually are not isolated, but actually are part of binary or tertiary, three-star systems. And so this is not just a hypothetical or a random discussion that we're going to have today. It's actually relevant to a majority of stars in the universe. So let's get to it. So, as I said, so far we've spent quite a lot of time actually on discussing the evolution of isolated stars. So you have a star form by itself, evolve by itself, and die by itself. And for low mass stars, that means moving from protostar to true star along the Hayashi track on the HR diagram, then spending a long time on the main sequence, or at least several billion years typically, then becoming a red giant after exhausting the hydrogen in the core, then moving along the horizontal branch after the helium flash, then moving on the giant asymptotic branch, and then eventually losing half your mass or so in the form of a planetary nebula, with the remnant being a white dwarf, a degenerate carbon-oxygen sort of remnant that's very hot but doesn't have any further source of nuclear energy, no fusion occurring, and so it just slowly cools off and fades into oblivion. So that's the story that we've told for a week and a half or so now. But we're going to add to it now, because now we're going to consider situations where you have the physics is all the same, right? The evolution kind of wants to be the same, but now we're going to add in a binary star, a binary partner to the star that's evolving, and we're going to see how does that change things. So the first step that will help aid in the discussion we're going to have is to introduce the concept of Roche lobes. And a Roche lobe is just, essentially a gravitational sphere of influence that a star has. So, we have already mentioned quite a while ago now, but when we introduced the concept of binary stars, we made the point that both binary stars will orbit around their common center of mass, right? So if the stars happen to be of equal mass, then then that center of mass is their geometric center. It's just the midpoint between them. But more likely, they will not be exactly equal masses, and so you'll have one larger star, more massive star, and one less massive star, in which case the center of mass is actually closer to the more massive star. And so the upshot is that the more massive star will have a greater sphere of influence, will have a greater Roche lobe. And so the Roche lobes are drawn here, which again just kind of give you a picture of where each star's gravitational influence dominates. So if you're inside one Roche, the large mass Roche lobe, that means the large mass is dominating. If you're nearer the small mass, close enough to the small mass, then its gravitational field will dominate. And so that's just a definition. But it's something that we're going to use going forward. So so keep it in mind. This is what a Roche lobe is. So now let's use the concept of Roche lobe to help understand what's going to happen as evolution, as binary stars evolve. And we're going to start off by noting that when binary stars form, they form at essentially the same time, right? They're forming in something like a giant molecular cloud, forming out of the same cloud of gas, and forming at very much the same time. So in this case, we're considering a pretty generic situation where one star is a little more massive than the other. And so again, that more massive star has a slightly larger Roche lobe. So each star, now that they've formed, they start evolving, right? The nuclear fusion is going on in the core, hydrogen is being converted to helium through the triple alpha process, and they're evolving. But not at the same rate, right? Because as we've said several times, and so hopefully it's sinking in, the more massive a star is, the hotter the core will be, the faster the nuclear reactions will occur in the core, and so the faster that star will evolve. And so what that means is that if we can just skip several billion years, the more massive star, which in this slide is designated star 1, will reach the end of its main sequence lifetime before star 2 will. Okay, so and that's depicted here by virtue of star 1 turning red, right? It's turning into a red giant. And eventually, as it moves up the red giant branch, it gets larger and larger, and eventually it actually spills out over outside its Roche lobe, which is kind of it's a little bit crazy to think about, but these things do really get monstrously large. And so what that means is that the surface of or the outer layers of star 1 are now dominated. The gravitational field of star 2 is actually stronger there than is the gravitational field of star 1. And so what does that mean? That means star 2 is now going to start stealing some of that material. Okay? So star 2 steals material from this red giant partner, star 1 now. And as it does that, it gets hotter, it has more fuel to burn, and it becomes more luminous, but it's still on the main sequence, right? So star 1 has evolved to the point that it's now a red giant. It's on the red giant branch. Star 2 is getting hotter. Things are changing. It's getting more massive, more, higher temperatures, more luminous, but it's still on the main sequence because the nuclear reactions in the core are still proton-proton chain. Eventually, star 1 finishes its evolution because, again, it's a massive star. These are still low mass stars, so it's not a high mass star, but it's more massive than star 2. So it finishes its evolution. It gives off its planetary nebula. It settles down as a white dwarf. And now you have a situation where you have a white dwarf as a binary partner of a now hotter main sequence star, right? And if you look at the schematics here, star 2 started off yellow, and now it's blue because it's gotten more massive and it's gotten hotter, okay? Now, it doesn't mean that's always going to happen, right? But it will, as it gets more massive, it will get hotter. And so if it starts as an M-class star, it might move up, a class or two, just depending upon the details. But now star 2 starts to evolve, right? It finally finishes proton-proton chain reactions and reaches the end of its main sequence lifetime. So what happens then? Well, it too now expands. It starts transitioning into a red giant, moving up the red giant branch. The outer surface expands, overflows its Roche lobe, and now some of its material starts getting stolen by the white dwarf remnant from star 1, right? So now we've just reversed the process. Over time, the hydrogen that's now being stolen from the red giant star 2 onto the surface of the white dwarf builds up. And so you get more and more hydrogen building up on the surface. And eventually enough hydrogen builds up that the outer layer of that star, which had no hydrogen when it started as a white dwarf, right? All the hydrogen has long since been gone. It's just carbon and oxygen in a degenerate hot, sort of white dwarf. Now you're putting hydrogen on the surface again. And so eventually it gets hot enough that nuclear fusion can occur again. And so now you have a blinding flash where all of a sudden you ignite in a nuclear sense the proton-proton chain again on the surface. And this produces an extremely bright explosion known as a nova. Don't confuse that with a supernova, which we will get to very shortly. This is a nova. It happens very quickly. And more or less all at once. I mean, it's not a split second, but essentially you build up hydrogen on the outer surface of the white dwarf. Eventually it gets hot enough and you get enough of it gets dense enough that these hydrogen nuclei or these protons start colliding. The strong nuclear force does its thing, and fusion occurs. And so it's an exciting thing for us. This is something that we can see, and so it's something that you would never see in the context of an isolated star, right? So if you were wondering why on earth would the presence of a binary partner impact the evolution of a star, the reason is that it steals material, it steals matter. And a nova is one, very sort of prominent result of that theft. So what does a nova look like? I said it's exciting. Astronomers get excited about these kinds of things. Here's a picture of a white dwarf before a nova, where it's just a white dwarf. And this is the same part of the sky after, or in the midst of a nova. So you can't miss this, right? If you're looking at at the right place in the sky and a nova occurs and you're paying any attention as an astronomer, you're going to see it. And the reason you're going to see it is that nova can shine more than 1,000,000 times brighter than the star itself for a period of several hours. So as I said, it's not a split second, but in astronomical time, this is, less than a blink of an eye. Remember, you spent maybe 10 billion years on the main sequence, and now you're talking about just shining 1,000,000 times brighter than you ever did before, but for only a few hours. So this is why, from an astronomer's perspective, if you want to observe this, you've got to be looking, you have to be looking at that part of the sky. In reality, what will happen is that when one of these things is seen, it's immediately announced, and then lots of astronomers around the world point their telescopes at that part of the sky to collect the data for as long as it's there, and then, pretty soon it's gone. But it's exciting while it's there. So I've told you now that a white dwarf that forms in the context of a binary or tertiary star system it may have a more exciting existence than your isolated white dwarf, just because if it's able to steal some additional mass, some additional hydrogen from the envelope of its partner, then it can give rise to a nova. And in fact, this can happen multiple times with the same star. You can imagine a situation where a white dwarf steals some mass, eventually gets enough hydrogen to nova, and then after a few hours, all of the hydrogen has fused basically, and then it goes back to being, a normal white dwarf again. But then it can continue to steal more mass, and it can nova again. And this can repeat, for in principle any number of times. But there is something that's going to stop it eventually, and the reason is that there actually is a mass limit to a white dwarf, a fundamental limit to how much mass a white dwarf can have. And so the next thing, and that's the topic we're going to turn to now, is to consider what is it that would limit a white dwarf's mass, and what happens if a white dwarf somehow obtains more mass than is allowed. So the key to answering this question is to go back to a concept that we've talked about a handful of times, which is the hydrodynamic stability or equilibrium of a star, and in this context, a white dwarf. So what is it that is maintaining the stability of the white dwarf? And as always, it's a balance between two forces. On the one hand, you have gravity tending to collapse the white dwarf, and on the other hand, you have an internal pressure that sustains it against that gravitational collapse. And we've talked about this a handful of times, and typically ask the question, well, what is responsible for this internal balancing force, the internal pressure? And the answer has been different in different contexts, right? In the context of a main sequence star, the core of the star has an internal pressure largely due to the radiation that's coming out of the nuclear reactions, which is why when all of the hydrogen is exhausted, the core then collapses because you've taken away the internal pressure. Well, white dwarfs are also supported by internal pressure, but in that context, the internal pressure is due to electron degeneracy pressure, right? And this is something that we've talked about a few times already, but just to kind of remind you, it's basically saying it's a really dense electron gas that is responsible for maintaining that stability. A white dwarf is quite small, in terms of stellar sizes. Remember, it's similar size to the Earth, but it has a mass, of half the sun or more, for example. And so it's in terms of the nuclei that are there, we've said, that it's oxygen and carbon largely. But of course, there are also a whole bunch of electrons, and there always have been, right? We don't talk about electrons very often when it comes to stars, but occasionally we do, and it's important to remember they're there, because if they weren't, then you would have a massive, you'd have the star that would have a massive positive charge, and it would blow itself apart. So if it weren't for the electrons, this thing would be electrically charged, and it would be horribly unstable. But they do something even more important than the electrical stability or the electrostatic sort of stability in the context of white dwarfs, because it's not their charge that plays the important role here, but it's their fundamental quantum mechanical properties that give rise to this electron degeneracy pressure. Okay, and so I mentioned this before when we first introduced this concept. This is something that, by virtue of being fundamentally quantum mechanical, you could, in order to really understand it, we need to do quite a bit of background in quantum mechanics. And that would be, I would love nothing more. I highly encourage you to go find a class in quantum mechanics, or talk to me offline. I'll give you a crash course if you like. But for us, it's enough to just know it's electron degeneracy pressure. You really can't squeeze electrons easily at all, because because you just can't. But it turns out that even though electron degeneracy pressure is extraordinarily strong, much, much higher than any other form of pressure that exists in the stars that we've talked about so far, there still is a limit to that too. Okay, and you get closer and closer to that limit as the white dwarf gains more and more mass. So if you imagine a white dwarf stealing more and more hydrogen from its companion, then going nova, transforming the hydrogen into helium, then stealing more hydrogen and doing it again, and so on, the mass of that white dwarf slowly grows, and eventually it may reach or approach the limit known as the Chandrasekhar limit. Chandrasekhar is a phenomenally important Indian physicist, as a matter of fact, that basically was a one-man show leading the charge in astrophysics, in theoretical astrophysics at the time that he lived. So there's a whole lot of interesting physics that he's done. But so it's pronounced Chandrasekhar. But so if the white dwarf reaches the Chandrasekhar limit, that's the point at which, even though this electron degeneracy pressure is very, very strong, gravity is going to win. And so that limit happens to be 1.4 solar masses. So 1.4 times the mass of the sun is the maximum possible mass of a white dwarf. If you're less than that, it's fine. It will be able to reach an equilibrium where the electron degeneracy pressure balances out gravity. But if you are greater, if the white dwarf has a greater mass than 1.4 solar masses, then gravity will win, and it will continue to collapse that white dwarf. And it will no longer be a white dwarf, which leads us to the next question: what happens? And here's a really good picture, nice eye candy, to ask you exactly that question. Well, what happens when you exceed, or when a white dwarf exceeds the Chandrasekhar limit? And it's pretty exciting. As a white dwarf gains mass, again, stealing mass from its binary partner, it gets hotter and hotter until eventually it does, in fact, get hot enough that the carbon and oxygen in the white dwarf are able to fuse. We've seen a few different kinds of fusion already. Obviously, a lot of proton-proton chain. We've talked about the triple alpha process as well. But so far, we've said the carbon and the oxygen, by virtue of having 6 protons and 8 protons respectively in their nuclei, the electrostatic repulsion is just too large to get those nuclei close enough for the strong nuclear force to initiate those fusion reactions. But if you keep pouring mass in and you keep increasing the temperature, eventually you can ignite in a nuclear sense, initiate nuclear fusion reactions with the carbon specifically. And they don't actually call it a carbon flash. At least I've never actually come across that term, but that's kind of what happens in the, analogous to the helium flash, where the degenerate helium core of a red giant starts going gangbusters all at once and fusing in the triple alpha process. Something very similar happens in the case of a white dwarf that exceeds the Chandrasekhar limit, where you have a runaway nuclear reaction of the carbon, and it happens so quickly that the star explodes. And if you thought there was a whole lot of energy released during the main sequence, or you thought there was a whole lot of energy released during a nova, which we said could make the star or the white dwarf 1,000,000 times brighter than it was during its main sequence lifetime, the energy released in this sort of white dwarf explosion is really mind-boggling. And we talked about nova, and I said it's not a supernova. Well, this is a supernova. And to be a little more specific, this type of explosion is known as a type 1A supernova, and it's one of the most energetic things in the universe. We don't observe these a lot. Astronomers and physicists get excited when we do see them, but they really are something, because it's, again, you've reached the end of the stellar life. An isolated white dwarf just fades into oblivion, but if you have a binary partner and you're able to steal, and the white dwarf is able to steal enough mass, then you can ignite the whole carbon, all the carbon at once, basically. Massive amounts of fusion in a very, very dense, core, and it explodes. So that's worth, unfortunately we don't see these things happen in real time usually, in terms of they're very far away, so we can get signals from telescopes, but if something like this were to happen in our astrophysical or astronomical backyard, it would be really cool, and it's cool in any case. So because they're not so frequent, when they happen, we take note, and people have actually taken note historically. And it was easy to do relatively, because these things are absurdly bright. A type 1A supernova is 10 billion times brighter than the sun. Okay, so that's one with 10 zeros behind it. And as a result, if a star is in our galaxy and it supernovas, we would be able to see it during the daytime, and at night it would be as bright as the full moon. And so as a result, we started off this class saying that astronomy is the oldest science, right? That was my claim, one of the first slides of the semester, because all you got to do is walk outside after sunset and look up, right? It turns out that to observe a supernova, you don't even have to wait to sunset. You can see this thing during the day. And so there are quite old observations of supernova. There's one particularly famous one in the year 1054, which gave rise to the Crab Nebula, which is a well-known nebula that you can Google up and find some nice pictures of. There was another one even earlier than 1054 in 1006, so I guess the 11th century AD was a good century for supernovas. Here's a picture of the remnant of the supernova, and the fact that we see this afterglow, and the fact that it still exists, tells you that even though the star exploded, we first observed it over 1,000 years ago. I don't know how many light years away this particular supernova was, so I don't know how long it took the light to travel. But but obviously it's still kind of the stuff is still moving through space. That explosion, it throws, basically just obliterates the white dwarf, and throws all of that material out into space. And as that stuff moves through interstellar space, it will pass through material, like clouds of gas, in the interstellar medium. When it does, it creates what's called a shock wave, and or it is a shock wave, and will heat up the gas that it travels through, extremely high temperatures extremely quickly, and can actually help seed stellar formation in that way. So there's a lot of interesting physics that goes into the study of these types, both of the explosions themselves and then what the effects of those explosions are in the interstellar medium. And here there's some words on the slides that just kind of repeat what I said. So if you prefer to pause me or mute me, you can read the slide instead. And so we've said we can see these supernova during the day if they happen to be in our galaxy, but they're so bright that if they're not in our galaxy, we may not be able to see them during the day, but we can still see them very, very clearly at night. So here's an example of a supernova in some galaxy with a nondescript name, but you can see there's a really bright, really bright former star there, right? Not a star, in fact, not even a thing at all after you see this, but it went out with a bang. And here's another image of a supernova in the not very excitingly named galaxy M51. You might not see it if I didn't point it out to you, but you can certainly see there's this, very bright dot there that is conspicuously absent on May 9th, but it shows up very clearly on July 10th. And so yeah, I understand it would be a lot more exciting if these things were closer. The idea of being able to see one during broad daylight would be pretty cool. As you may or may not recall, there was, not too long ago, there was speculation that a red giant named Betelgeuse, which is in the constellation of Orion, might go supernova, and because it had some noticeable intensity variations on Earth, and it's known that it's a red giant now. It's a massive star actually, so we're talking about low mass stars here, so it's a high mass star, so it's a little different. But anyway, that's the most recent speculation about a supernova we might see. But most supernovas we have no warning of, and in fact, given how bright they are, it's entirely possible, even probable, that if we were to see a supernova, that it would be a star that we didn't even know existed until it supernovaed, right? Because if it's somewhere else, if it's not, it could easily be not visible from our vantage point now, but if it becomes 10 billion times brighter as it explodes, all of a sudden you can imagine being able to see it quite clearly. So keep your eyes peeled, but don't hold your breath. So there are a couple of theories actually regarding the details of type 1a supernova. One is what I've described, and there's no question that what I've described would occur. I mean, this is something that will happen in nature if you have binary stars, which obviously we do, and if one turns into a white dwarf, which we know it will, and eventually exceeds the Chandrasekhar limit, it would explode. Okay, but there is another theory for what might produce type 1a supernovas as well, and that is, it's a little more exotic, and it has to do with the possibility of two white dwarfs spiraling into each other and colliding. And so in this case, rather than having one white dwarf and one red giant, for example, and the white dwarf stealing mass and then exploding, in this case you actually have two white dwarfs that end up colliding and merging. And so it's a different mechanism, but it achieves the same result, which is that now all of a sudden you've got a white dwarf that exceeded the Chandrasekhar limit. So the big difference is that in this case, where you have colliding white dwarfs, it happens very quickly, right? As opposed to a gradual accretion of mass that we talked about in the past. But again, nature doesn't care. What nature cares about is, can the electron degeneracy pressure balance the gravitational force? And the answer is only if the mass is less than the Chandrasekhar limit. So however white dwarf manages to exceed the Chandrasekhar limit, once it does that, an explosion is going to occur. So as I said, the verdict is still out. Lots of research and observations are going on to try to answer the question of what exactly is responsible for the type 1a supernovas that we observe. But either of these things are possible. Okay, so we're gonna wrap it up with this slide, and this finally, right, brings us to the end of our discussion about the evolution of low mass stars. But the question that I want to leave you with, and I won't leave you hanging, I will actually answer the question before cutting you loose, but is the following. So I've just made the claim that white dwarfs cannot have masses greater than the Chandrasekhar limit. So 1.4 solar masses is the maximum possible white dwarf mass. Any greater than that, and gravity is going to overwhelm the electron degeneracy pressure, and it's going to collapse until and heat up enough that it will explode. How is it then that both A and B type stars, which again, these are on the more massive end, on the hotter end, but of the low mass stars, but still low mass stars, how can they possibly end up as white dwarfs? Because we know they have masses greater than 2 solar masses. How is it possible, or is it possible, for these stars to end up as white dwarfs? And before pausing to give you time to think, I will tell you that it is possible. I will tell you that we know, based upon the distribution of stars in the universe, how many M-class, G class, A and B class stars there are, and how many white dwarfs we observe. We do know that A and B class stars can end lives as white dwarfs. So the question is, how is that possible, given that their initial masses are greater than 2 solar masses, which is quite a bit higher than the 1.4 solar mass limit of Chandrasekhar. So I'm going to pause for my usual 30 seconds. As always, you're welcome to pause me indefinitely, but I won't leave you hanging. I will give you an answer before I wrap this lecture up. Okay, well, the key is to remember that when a star forms, it has some initial mass. But by the time it reaches the white dwarf stage, it's lost a considerable amount of that mass, right? Up to half of its mass in the form of a planetary nebula. And so an A or a B class star could form with, say, 2.5 solar masses. But if it's lost half of its mass by the time that it gets to the really end of its life, then it may have fallen underneath the Chandrasekhar limit. And that's really the key. When we say that the Chandrasekhar limit says what is the maximum possible white dwarf mass, that's the mass that's left in the remnant after, at the end of the star's life. Whatever mass has been shed into the interstellar medium, that doesn't count. And so for that reason, you can start off with almost even 3 solar masses, and then just lose enough to get down to the white dwarf. To the white dwarf limit. or below the Chandrasekhar limit. So that's the key. So now you can sleep peacefully at night and not be kept up thinking about that. So thanks for your attention. I appreciate you sticking it out and making it to the end of our discussion of low mass stars evolution. As you might expect, we're going to move on next and spend a couple of lectures discussing the evolution of high mass stars, which are certainly going to bear some similarities, but there are also some important differences and some exciting differences because, as you might expect, more massive stars can produce more exciting endings. And so we really are now getting ready to transition into the last kind of third or so of the course, where we're going to finally start talking in some detail about some of the more exciting and exotic astrophysical objects that you may have heard of, that people talk about even on pop culture, television shows and so on. So stay tuned. I appreciate you having hung tough in the course so far. Hopefully you'll find that all of that was worth your while, and we'll have some interesting stuff going forward. So enjoy the rest of your evening or afternoon whenever you're watching this, and I will look forward to seeing you back here for Lecture 20.